Mid-February 1943, Sidi Bouzid, Tunisia, a captured M4A1 Sherman rolled to a stop in the desert. Its white American star still visible under a freshly painted German cross, while officers from Heavy Panzer Battalion 501 crowded around with notebooks ready. This one American tank, taken intact and still working after the fight at Sidi Bouzid, would spark a crisis of confidence among German engineers that rippled through their tank programs. To war's end, the mouth of armored warfare was about to change, not because of thicker armor or bigger guns, but because of something Germany had never prioritized: automotive engineering that refused to quit. The tank's name, War Daddy 2, was painted on its hull. Its serial number, USA 3,067,641, showed it was built by Lima Locomotive Works and assigned to Company G, 1st Armored Regiment, 1st Armored Division. A German recon team then drove this Sherman 350 kilometers across rough North African ground to the port of SFAX over 4.5 days. And every kilometer contradicted German assumptions about American industry. The engine never overheated. The transmission stayed smooth. The final drives remained strong. German crews, used to frequent breakdowns even on short moves, watched uneasily as this enemy machine just ran through heat, sand, and punishment that often sidelined their own vehicles. At SFAX, War Daddy 2 was loaded on a ship bound for Germany with strict orders from the Army Weapons Office, delivered to Kummersdorf intact and operational. German intelligence had heard bits and pieces about American production, but seeing one of these tanks up close made the numbers real in a way paper never could. The Sherman was mass-produced at a scale Germany could not match, and it embodied automotive principles Germany had not mastered. As the ship steamed north, Wehrmacht engineers prepared tests that would force them to face hard truths about their limits. And America's strength stood in spring 1943 at the Kummersdorf Proving Ground in Brandenburg. War Daddy 2 rolled off a rail car, tagged as Zugkrafts to 159 with license plate WHO589 for one. Test engineers had already stenciled armor thicknesses and angles over the hull and turret for a thorough evaluation. Kummersdorf, about 25 kilometers south of Berlin, was the main test site for German and captured Allied gear. Here, careful engineers measured everything from track tension to transmission losses and wrote exhaustive reports. The Sherman was about to face the most complete automotive exam German experts could build. Specialists from different branches began with a detailed inspection, photographing each component, measuring clearances with precision tools, and noting construction methods that looked shockingly straightforward compared to German practices. The transmission drew immediate attention. German tanks used straight-cut gears that needed tight tolerances and frequent care. But the Sherman used herringbone-cut gears that spread load across many teeth at once. This design, standard in American automotive factories since the 1930s, gave excellent durability with less finicky precision. German engineers had judged herringbone gears too hard to mass-produce given their machine tools and workforce. Americans had been making them by the thousands. Trials started with controlled driving over obstacles and rough courses, logging fuel use, engine temperatures, and transmission behavior under different loads and surfaces. After each run, parts were opened and wear patterns studied for signs of stress, poor oiling, or weak design. The results broke a core German belief about performance versus reliability trade-offs. The Sherman did fine in every area and excelled where German tanks repeatedly failed. Long, continuous operation without maintenance. The powertrain tests revealed the deeper split in design philosophy. The Sherman had 5 forward gears and 1 reverse, with gears 2 through 5 synchronized. So drivers did not need to double clutch during normal use. That made it almost as easy to drive as a car, so training could be short. German drivers had to learn touchy double clutch techniques and careful throttle work to avoid damage. The Sherman assumed ordinary soldiers with basic car knowledge would run it, while German designs assumed highly trained specialists. The Continental R975 radial engine in this Sherman also impressed. It held power across temperature ranges that would make German engines overheat or bog down. The simple cooling system worked very well. The air filters handled desert sand without constant clogging. Each system showed a practical mindset. Make it work in real conditions, not just on paper. On June 6th to 7th, 1943, at the Hillesleben Range, Armaments Minister Albert Speer oversaw a major conference with industry leaders and senior officers. That included hill climb trials. War data lined up next to Germany's newest vehicles, including a fresh Panther A USF-D and a Ferdinand and tank destroyer with an advanced electric transmission. Speer needed to see where German designs stood and what the Americans could actually produce. The answers would be uncomfortable. The Sherman climbed smoothly, the synchronized gearbox shifting cleanly, the engine pulling without drama, and the driver showing how easy the tank was to handle. The Panther, despite its powerful 700 horsepower Maybach HL-30, only matched the performance with more difficulty. The 65-ton Ferdinand stalled halfway up, dead in front of dozens of officers and executives as crews struggled to restart it. Later, Speer wrote about reports from Italy in October 1944 that praised the Sherman's cross-country mobility. Units said Shermans climbed mountains German experts had called impossible for tanks. He credited the Sherman's strong power-to-weight ratio and said its cross-country ability on level ground was clearly superior to German tanks, a point the 26th Panzer Division specifically reported. These comments carried weight and appeared in a careful article in Das Reich on June 27, 1943, calling the Sherman a noteworthy North American achievement and a praiseworthy product of their steel industry, pointing out serial production standards that met the almost arrogant demands of the U.S. auto sector, and mentioning the gyro-stabilized gun as a world first. Publicly, it was cautious. Privately, alarms spread through German engineering offices. American tanks were not merely adequate. They were fundamentally better suited for sustained field use. Back at Kummersdorf, testing continued through summer and fall of 1943. Long-range trials showed the Sherman could exceed 2,000 kilometers before major maintenance, roughly 4 times what early Panthers managed in real field conditions. Measured transmission efficiency beat any German tank, with less power wasted in the drivetrain. The synchronized gearbox made shifting smooth without double clutching or careful rev matching. The final drives posed another shock. Panthers used a final drive setup inherited from the Tiger's concept, with straight-cut gears and housings that could not handle a 45-ton tank's loads, leading to frequent failures. Field units in North Africa and on the Eastern Front reported final drives breaking after surprisingly short movements, sometimes under 100 kilometers. The Sherman's final drives, built with the same herringbone approach, rarely failed even under prolonged combat stress. Decades later, restorers would find Sherman final drives that needed no major repairs after years in storage, proof of generous design margins. By late 1943, Kummersdorf had compiled enough data for internal reports circulated to senior officers and the Armaments Ministry, and they were sobering. The Sherman showed an American automotive maturity that Germany lacked despite theory and scientific skill. Mass production allowed looser tolerances that would be sloppy in German precision terms, yet produced more reliable vehicles that worked better in the field. Interchangeable parts meant repairs were fast with basic tools and minimal special training. German vehicles often needed factory-level precision and expert tools. The American goal was to keep vehicles running, not to chase peak performance that looked good on paper but could not be sustained in combat. German assessments also recognized American industrial advantages beyond raw numbers. The US had decades of broad car ownership, so automotive skills and expectations were widespread. In Germany, cars were luxury goods, and the promised Volkswagen program had delivered fewer than 1,000 civilian cars by 1939. This gap in civilian automotive maturity translated directly to tank design. Americans built tanks maintainable by mechanics with civilian training. Germans built tanks that demanded specialists and constant expert attention. Field reports through late 1943 and early 1940 made the reliability contrast impossible to ignore. Panthers needed strict rules to avoid breakdowns. Drivers were told to shift as little as possible because frequent shifting damaged gearboxes. Third gear failed, so often manuals warned against using it unless necessary. Panthers could not turn while reversing without risking transmission failure. Pivot turns were only safe if ground resistance matched on both tracks, limiting tactics. Debris in the running gear could jam a drive sprocket and cost hours to clear. This was despite skilled workers and the best materials Germany could spare. Meanwhile, US tanks came from GM, Ford, and Chrysler engineers applying proven mass production methods. They used commercial components where possible and standard supply chains. Transmissions came from Caterpillar, Buick, and Ford to identical specs, with truly interchangeable parts that could be mixed without adjustments routine. In the American auto industry, but rare in Germany, where each maker's small differences harmed interchangeability. More captured Shermans arrived at Kummersdorf in 1943-44 from British units in Italy and Soviet units in the East. and each went through the same trials, building a database across models and production runs. German engineers paid special attention to the British 17-pounder armed Firefly, which solved the Sherman's main firepower weakness. The large turret ring allowed the bigger gun with minimal changes, showing growth room designed in from the start. The Panther, rushed to counter the T-34, had no similar growth capacity without major redesigns. Reliability trials expanded to long cross-country runs, logging every incident and comparing those to real Panther and Tiger field reports. The numbers were stark. Panther operational readiness averaged below 40% for most of 1943, with some units as low as 20 to 25%. And some battalions at times had fewer than 1 in 5 tanks combat ready. Shermans kept much higher readiness almost everywhere. Specific German reports show Panthers at Kursk in July 1943 at only 16% operational, with breakdowns destroying more combat power than enemy action. By December, readiness was only 37%. February 1940 for again 37%. April 50%. May finally 78%. Even then, the best Panther rates never matched what Shermans achieved out of the gate. By December 1943, the pattern was clear. Sherman diesel engines could exceed 3,000 kilometers with proper care. Panther engines struggled to reach 1,000 kilometers even after fixes. A March 1940 report called 700 to 1,000 kilometers acceptable, which merely brought Panthers to about a third of the Sherman diesel's endurance. Sherman transmissions needed little attention between overhauls, and the synchronized gears reduced driver-caused damage. Panther gearboxes needed constant care, and third gear failures were so common drivers skipped from second to fourth. Sherman final drives stayed reliable, where Panther final drives often failed. Within 100 to 200 kilometers, frontline German use of captured Shermans reinforced Kammersdorff's findings. Desperate for vehicles that simply worked, German units happily used any Sherman they got. Unlike captured T-34s, which Germans often modified heavily, Shermans were used as is. They needed no major changes because they were sound designs. German crews with long breakdown histories in their own tanks commented often on the Sherman's reliability. Reports said Sherman crews could focus on tactics and fighting, while Panther and Tiger crews constantly feared breakdowns en route or during missions. The 10th SS Panzer Division, for example, captured 12M for A3 South at Hattenrittershofen-Elsass during Operation Nordwind in January 1945, forming them into a 13th company that served to war's end. These tanks ran reconnaissance and mobile reserve roles that demanded long, reliable movements. German commanders admitted what Kammersdorff had proven. American tanks could be counted on to function when needed. In the final months, that mattered more than raw firepower or armor. A Sherman that arrived at the fight with a working gun was infinitely more useful than a Panther, with a bigger gun broken down 20 kilometers behind. As 1940 began and more equipment arrived, engineers tested the M for A1 with the Continental R975, the M for A2 with twin GM 6046 diesels, and the M4A3 with the 4GAAV8, which American crews often preferred. All variants shared the same core trait: excellent automotive reliability from sound engineering and quality manufacturing. The consistency across makers also impressed German engineers used to wide quality swings. Among their own factories, the diesel M4A stood out. The Soviets received about 4,100 of them, and many fell into German hands as fronts shifted. The twin diesels matched other Shermans in performance while using much less fuel, a critical edge as German supplies dwindled. German designers had tried diesel, but dropped it due to manufacturing challenges and fuel injection complexity. American factories built diesel and gasoline Shermans side by side without disrupting schedules, showing flexibility and sophistication Germany never achieved under wartime stress. In March 1944, General Heinz Guderian, Inspector General of Panzer Troops, reported Panther reliability had reached acceptable levels, engines lasting 700 to 1,000 kilometers, and final drive issues reduced by design changes and better production. But this success only brought Panthers up to where the Sherman had been since 1942, highlighting how far behind German development had fallen. Meanwhile, resource shortages and air raids hammered German tank production bottlenecks. On April 27 to 28, 1944, RAF bomber Command heavily hit the Maybach engine plant at Friedrichshafen and destroyed the adjacent ZF gearbox factory with a 322 aircraft raid, described as the most damaging of the war for German tank output. Engines and transmissions stopped for 6 months, and when they started again, quality had dropped sharply. Forced labor, used more as German workers were drafted, led to quiet sabotage, cigarette filters in oil channels, misfitted gaskets, and assemblies built without proper clearances. None of these issues touched Sherman production safely in the US, staffed by paid, motivated workers. The core difference between American and German tanks was not knowledge, but industry and priorities. German engineers understood the theory. They simply did not apply it consistently, chasing impressive specs at the expense of reliability. The Panther's excellent 75mm KWK-42 and strong frontal armor came with a powertrain straining under 45 tons. The Tigers might required complex, frequent maintenance by experts. If Germany could have outproduced and outspared those designs, the trade-offs might have been worth it, but they could not, especially as bombing and shortages mounted. American engineers, raised in mass-market automotive design, built tanks in the tens of thousands that ordinary mechanics could maintain. The Sherman used proven commercial ideas and components. Its electrical system even had a backup generator to power turret traverse, with the main engine off, seemingly a luxury to German designers, but priceless in combat, especially on slopes where German turrets sometimes froze when engines stalled. Such features did not appear in German specs because they were not priorities next to armor and gun. By spring 1944, units on all fronts reported rising mechanical trouble as German manufacturing quality slipped, and spare parts grew scarce. Panthers had to be moved by rail if the trip was over 100 kilometers. Because their final drives could not survive long road marches, orders restricted movement to save precious life for combat. The Berger Panther recovery vehicle, built on the Panther chassis, suffered the same weaknesses as the tank it was meant to tow. Some reports said 70% of tank losses were from breakdowns, not enemy fire. Meanwhile, Sherman production surged to levels Germany could never approach, 49,320 for built, more than all German tanks of all types combined. The British Commonwealth received thousands. The Soviets got over 4,000 diesel variants. Chinese forces in Burma used Shermans effectively against Japanese armor that lagged behind both American and German standards. Everywhere, the same pattern appeared, with proper maintenance. Shermans kept running where German tanks failed. German crews who used captured Shermans praised their automotive strength in letters and post-war interviews. On the Eastern Front, mechanics even said, the complicated Chrysler A57 multi-bank 5 small engines tied together was easier to troubleshoot than German tank engines that needed specialized know-how and tools. The 4GA AV8 looked outstandingly reliable to mechanics accustomed to Maybachs that needed constant valve, ignition, and carburetor adjustments. The GM twin diesel, rejected by the US Army as less reliable than gasoline for its own use, outperformed any German diesel made for tanks. The Sherman's generous design margins brought more benefits. The basic transmission and final drives built for a 30-ton M4 with 400 horsepower needed no major changes to handle the 42-ton M4A3E to jumbo, and those same parts reliably carried 650 horsepower from test engines. German engineers saw waste in such overbuilding, but Americans' new extra margin created growth potential and battlefield reliability that paid off over the tank's life. By summer 1940 in Normandy, German commanders understood their disadvantages went beyond single tank matchups. American artillery, air power, and logistics overwhelmed German forces regardless of specs or tactics. The Sherman's reliability meant American armored units could attack, sustain combat, pursue, and reset quickly without long maintenance pauses. German panzer divisions had to guard every kilometer of movement, knowing each trip burned through failing components. Operational availability decided who could keep the pressure on and who had to ration scarce fighting power. The 150th Panzer Brigade, built for infiltration during the Battle of the Bulge, tried to get captured American vehicles for disguise. They wanted Shermans specifically for their reliability, but got only two, and only one was truly serviceable. It never reached the fight because of massive traffic jams, a mission requiring long, breakdown-free running behind enemy lines could only trust American vehicles. German tanks, even when fully operational, could not promise the sustained performance such missions needed. Finally, on January 23, 1945, the Panzer Commission admitted the automotive disaster in an official report. Hundreds of defective final drives across Panzerivs, Panthers, Tigers, and about 200 failures in Hetzers. General Wolfgang Tommel, Guderian's chief of staff, wrote bluntly that orderly tank use was impossible. Crews lost confidence. and some abandoned entire vehicles over final drive fears. German tanks built to impress on paper failed the essential requirement, being mechanically reliable enough to reach a fight and complete a mission. As the Red Army closed in, Kummersdorf prepared to evacuate. Engineers packed records and shipped them west. Some captured tanks, including at least 2 Shermans, were thrown into last-ditch fights near Berlin. Those Shermans kept running until destroyed by enemy fire or abandoned for lack of fuel. Panthers and the few remaining Tigers broke down at rates that shocked even veteran crews. The story of War Daddy II and the many Shermans tested at Kummersdorf is a clear portrait of industrial disparity. German engineers, in a system that favored theoretical perfection over practical utility, produced tanks that looked great on paper but failed in prolonged operations. American engineers, applying decades of automotive experience, built tanks that were less sophisticated in some ways but ran reliably under punishing conditions. In war, the weapon that works when needed beats the weapon that might be superior if it could get to the fight. Post-war US and British studies confirmed what Kummersdorf found: broken final drives, seized transmissions from poor lubrication or driver strain, and burned-out engines were as common as battle damage in German tank losses. Germany's obsession with headline specs blinded it to reliability and maintainability. They built machines a conscript mechanic could not keep running without experts, and a logistics system already cracking had to support countless unique parts. The lesson shaped West German thinking after the war. Designing the Leopard 1 in the 1950s, engineers emphasized reliability and easy upkeep over raw specs, studied American practices, and applied them deliberately. The Leopard 1 used robust powertrains with margin, straightforward maintenance, standardized components, and room-to-grow principles that made it one of the most successful Cold War tanks. The captured Shermans at Kummersdorf, especially War Daddy II with its name still on the hull, were more than trophies. They were proof that industrial maturity and practical engineering mattered more than chasing theoretical innovation, without regard to how to build, fix, and supply it. German designers bet that superior technology could offset fewer resources and fewer tanks. They were wrong. American designers built for reliability because logistics, maintenance, and sustained availability win modern mechanized wars. They were right, and it proved decisive. The reliability gap changed not just tactical outcomes, but how militaries understood industrial power's role in conflict. Germany entered the war with many technical edges and strong engineers, but lacked the industrial depth to mass-produce and sustain them on multiple fronts. The United States began with less sophisticated weapons in some areas, but had the factories to build them in overwhelming numbers, and the feedback loops to steadily improve reliability and performance. That industrial approach, embodied by the Sherman, beat German technical brilliance applied to small-scale production. America built nearly as many Shermans as Germany built tanks of all types while also arming allies, producing other weapons in vast quantities, and maintaining a high standard of living and economic feat Germany could not approach, especially once bombing intensified. The math was brutal but simple. A Sherman with his 75mm gun that showed up and fought was worth infinitely more than a Panther. With a better gun that broke down en route or needed 3 days of repairs for every day in battle, a battalion with 80% of its tanks operational could do what a 40% unit could never attempt. Reliability was not a nice to have. It was the foundation of combat power. German tanks failed that test again and again. American tanks passed it. Kammersdorf had proved this by mid-1943, even as Germany kept fielding Panthers and Tigers that looked terrifying, but could not be trusted to run. The Sherman did not win on armor or gun alone. It won through industrial superiority expressed as mechanical reliability, constant availability, and ease of maintenance. German engineers understood this from their own tests and wrote it down. But knowing a problem is not the same as solving it. Germany did not have the capacity to retool for reliability while fighting on collapsing fronts. Against enemies with deeper resources, America had already built reliability into its car culture and simply scaled it to war. War daddied to ordinary as one of 49. Zero told the whole story every time it drove without failing. Germany had chosen the wrong path by chasing specs over staying power, and the United States had chosen the right one by building machines that worked, that could be made and fixed in numbers, and that would still be running when the battle started.